So Kirchhoff's laws. So Gustav Robert Kirchhoff. So he lived in between 1824 to 1887. A German physicist published the first systematic description of the laws of circuit analysis. So to analyze the circuit, so Gustav Robert Kirchhoff published the systematic description of the laws. These laws are known as Kirchhoff's current law, that is KCL, and Kirchhoff's voltage law, that is KVL. So he published two systematic laws to analyze the electrical circuit or electrical networks, and that laws are Kirchhoff's current law and Kirchhoff's voltage law. So Kirchhoff's current law, or otherwise KCL. So definition is, in a lumped electric circuit, so electrical circuit should be lumped. So KCL and KVL is applied only for lumped circuit, not for distributed circuits. In a lumped electric circuit, for any of its nodes and at any time, the algebraic sum of all branch currents leaving the node is zero. So that is the definition of Kirchhoff's current law or KCL. In a lumped electric circuit, so it is applied only for lumped circuit, not for distributed circuit. So to analyze the distributed circuit, we have to apply electromagnetic field theory. So for any of its nodes, so KCL is applied. KCL, we can apply KCL at any nodes and at any time. So even we can apply this KCL for AC circuits. The algebraic sum of all branch currents leaving the node is zero. So currents at any node, branch currents leaving, sum of branch currents leaving the node is zero. So it is defined at a node. So KCL is defined at a node. So what is a node? So node is of two types, simple node and a principal node. So simple node means, so it is an interconnection of only two elements. So it is an interconnection of only two elements. So the point where two elements are connected, that point, the common point, is called as a simple node, whereas a principal node means it is an interconnection of at least three elements. So it is an interconnection of at least three elements. So here if we take this example, so here 5 branches are associated and there are 5 currents. Each branch has a current. So I1 is the current in this branch which is moving towards the node. I2 is the current in this branch coming towards the node. I3 is the current in this branch leaving the node. I4 is current in this branch leaving the node. And I5 is the current in this branch again leaving the node. So what is KCL is saying? So the algebraic sum of currents leaving the node is zero. So it is applied at the node. So if we apply KCL at this node, so here I1. So I1 is the current coming towards the node. So leaving current in this branch is minus I1. So that is very important. So if I1 is the current coming towards the node in this branch, then what is the current leaving this branch is minus I1. So similarly, I2 is the current coming, leaving current is minus I2. I3 is leaving, I4 is leaving, and I5 is leaving. So the algebraic sum of leaving currents at any node is zero. So minus I1, leaving current is minus I1, minus I2 is leaving current, plus I3 because I3 is already leaving. So plus I3 plus I4 plus I5 equal to 0. So here minus I1 minus I2 plus I3 plus I4 plus I5 is 0. So or simply we can remember this as, so for the currents coming towards the node, take negative sign, and for the currents leaving the node take positive sign and equate to that to 0. So minus I1 minus I2 plus I3 plus I4 plus I5 is 0. So if you rewrite these terms, so I1 plus I2 equal to, if you take minus I1 minus I2 to that side, so I1 plus I2 equal to I3 plus I4 plus I5. So here I1 and I2 are the currents coming towards the node, and I3, I4, I5 are leaving currents. So sum of entering currents, sum of entering currents equal to sum of leaving currents. So sum of entering currents equal to sum of leaving currents. So similarly, if you write currents as rate of change of charge, because I equal to rate of change of charge dq by dt, so I1 can be written as dq1 by dt plus I2 can be written as dq2 by dt, I3 can be written as dq3 by dt, I4 can be written as dq4 by dt, and I5 can be written as dq5 by dt. So under taking d by dt as common and cancelling on both sides, so we get q1 plus q2 equal to q3 plus q4 plus q5. So this is also one form of KCL. So q1 plus q2, which is nothing but sum of entering charges, is equals to q3 plus q4 plus q5. That is nothing but sum of leaving charges. So sum of entering charges equal to sum of leaving charges. So in similar manner, again q can be written as n into E. So number of electrons into charge of electron, where charge of electron q equal to, so charge E equal to charge of electron. So E is equals to charge of electron, so which is 1.602 into 10 power minus 19 coulombs. N is number of electrons. So if you write this charges in terms of N and E, so N1E plus N2E equal to N1E plus N4E plus N5E. So taking E as common in left hand side of the equation and right hand side of the equation and cancelling on both sides, we get N1 plus N2 equal to N3 plus N4 plus N5. So here N1 plus N2 is the sum of entering electrons, which is equals to sum of N3 plus N4 plus N5 is sum of leaving electrons. So next features. So features of the KCL. So KCL applies to any lumped electric circuit. So we can apply KCL and KVL only for lumped circuits, not for distributed circuits. It does not matter whether the circuit elements are linear, non-linear, active, passive, unilateral, bilateral, time varying, time invariant, etc. That is, KCL is independent of the nature of the elements. So we can understand this point by taking this example. So here there are 5 elements are connected to this node. 2 amperes is a current source, and this is a capacitor, resistor, inductor, and this is a diode. So here current in the capacitor is IC, which is coming towards the node. 2 amperes is coming towards the node. Current in the inductor is leaving. Current in the diode is leaving the node, and current in the resistor is also leaving the node. So if we write KCL at this node, so minus 2 minus IC, because that are the currents coming towards the node. So for currents coming towards the node, take negative sign, minus 2 minus IC. So IR and IL and ID are leaving, so that's why take positive sign, plus IR plus IL plus ID. And algebraic sum of leaving currents is 0, equate that to 0. So here 2 plus IC equal to IR plus IL plus ID. So KCL is independent of the nature of the elements. So here there are different types of elements. Resistor, inductor, capacitor are linear elements. Diode is a non-linear element, and this is a source. And these 4 elements are passive elements. So we can apply KCL even KCL is independent of the nature of the elements. So only one condition to apply KCL is, so elements should be lumped. So we cannot apply KCL and KVL for distributed elements. So current through a branch measures the rate at which electric charges flow through that branch, because current equal to rate of change of charge, I equal to dq by dt. So KCL asserts that charges do not accumulate at any node. So KCL asserts that charges do not accumulate at any node. In other words, KCL expresses the conservation of charge at every node. So KCL expresses the conservation of charge at every node. This is very important point for competitive examinations. So in similar manner, KVL, Kirchhoff's voltage law. So the basic definition of Kirchhoff's voltage law is, in any lumped electric circuit, for any of its loops at any time. So the algebraic sum of the branch voltages around the loop is 0. So here in any lumped electric circuit, so KVL is also applied only for lumped circuit, not for distributed circuit, for any of its loops. So here we are applying KVL for a loop or a mesh at any time. So even we can apply this for AC circuits. The algebraic sum of the branch voltages around the loop is 0. So it is defined in the loop. So KCL is defined at the node, whereas KVL is defined in the loop. So in this example, so this is a source and these are 4 passive elements which takes energy. So always current entering side, if it is a source, we are taking a negative sign, for current leaving side positive sign. And and here resistor, inductor, capacitor and diode are passive elements. So that's why current entering side plus, current leaving side minus, plus minus, plus minus, plus minus. If for source, current entering side minus, current leaving side plus. So here KVL, we can apply KVL for this loop. So here V is a source voltage, VR is the voltage across the resistor, VL is the voltage across the inductor, VC is the voltage across the capacitor, and VD is the voltage across the diode. So if you apply KVL for the loop, so we come across negative sign minus, and the source voltage magnitude is V, we come across positive sign plus, voltage across the resistor is VR, we come across positive sign plus, voltage across the inductor is VL, we come across positive sign plus, voltage across capacitor is VC, we come across positive sign plus, voltage across the diode is VD, and that algebraic sum is equal to 0. So here V equal to, if we rewrite this equation, V equal to VR plus VL plus VC plus VD. So features of KVL. KVL applies to any lumped electric circuit. It does not matter whether the circuit elements are linear, non-linear, active, passive, unilateral, bilateral, time varying, time invariant, etc. That is, KVL is independent of the nature of the elements. So KVL expresses the conservation of energy in every loop. So KVL expresses the conservation of energy in every loop.